next we are having a sp3d2 hybridization. The sp3d2 hybridization, as the name says, that here we have the 1s3p and 2d orbital. So 1s3p and 2d orbital, which undergoes mixing and recasting process, and after that produces total 6 new orbitals, 6 sp3d2 hybrid orbitals. The example for this sp3d2 hybridization is SF6 molecule, that is a formation of sulfur hexafluoride. Again, here the hybridization, the sulfur being a central atom will undergoes the hybridization process. So sulfur, whose atomic number is 16, undergoes hybridization, and we have 1s2, 2s2, that is, I'm writing directly the outermost shell configuration. It's a 1s2, 2s2, 2p6, 3s2, 3p4. So 3s2, 3p4. S have 2 electron and the p orbital have 4 electron. The first singly and then pairing. So total number of half-filled orbital in the case of sulfur is 2, but the bond form is total 6. So here the number of bond and the number of half-filled orbital does not matches with each other. So finally we have to write its excited state. So excited state, that is 3d, the electron will excite to 3d orbital. Okay, so the sulfur in excited state now. In excited state we will have a configuration 3s1, 3p3 and 3d2. The electron from this orbital as well as this orbital, both the electrons will jump, because if I am jumping only the electron from here, then only 4 half-filled orbital will obtain. So to get the 6 half-filled orbital, the electron from s orbital and p orbital both will jump to or excite to the 3d orbital. So now the new configuration is 3s1 after excitation is 3s1, 3p3 and 3d2. So finally we have 1s orbital, 3p orbital and 2d orbital, which undergoes mixing and recasting process. So sulfur in hybridized state we will have 6 half-filled orbital. The electron distribution will be same. So this is 6 sp3d2 hybrid orbital. From fluorine, the sulfur hexafluoride fluorine, whose atomic number is 9, so its configuration is 1s2, 2s2 and 2p5. So from fluorine, fluorine being a peripheral atom will not undergo hybridization, so it will have 2p5. That means from fluorine pz orbital undergoes mixing. The pz, from fluorine the pz orbital being a half-filled will takes part in a bonding. Now again d orbital is there, so we did not have to show the overlap. So directly we have only the geometry for the sulfur hexafluoride. So sulfur is going to be at the center. There is a total 6 fluorine atom. Out of 6 fluorine atom, the 4 fluorine atoms are oriented towards the corners of a square. So these are the 4 fluorine atoms. And there is a 2 more fluorine atom. These 4 fluorine atoms are present in a same plane, and that's why it is called as square planar. And 2 fluorine atoms are there which are perpendicular to the same plane, that is 1 fluorine will be here and the 1 fluorine will be here. So ultimately the geometry is and this one, and this is called the octahedral geometry. Octahedral geometry, where the 4 fluorine atoms are present at the 4 corners of this square planar square, and these are the 2 fluorine atoms which are making 2 pyramid, one above this 4 fluorine atom and the one below it. So that geometry which we get is called as octahedral geometry, or also sometimes use the word square bipyramidal geometry. Now in case of sulfur hexafluoride, we have this angle as also 90, as well as this being a perpendicular, this is also 90 degree. Let's see the same geometry in the animation form. That is, in animation you can see, observe that again the sulfur is at the center and the 4 fluorine atoms are oriented at the 4 corners of this octahedral. This is octahedral geometry, where you can see that 4 fluorine atoms are present on the 4 corners of the octahedron, and 1 fluorine is above the square and the second fluorine is below the square. So this is octahedral geometry of SF6 molecule. So all the molecule which undergoes sp3d2 hybridization, they forms octahedral geometry if there is a no lone pair electron. Next we are having a sp3d3 hybridization. The sp3d3 hybridization means where 1s orbital and 3p orbital and 3d orbital undergoes mixing and recasting process and produces total 7 new orbitals, and each orbital is called as sp3d3 hybrid orbitals. Now the example for this sp3d3 hybrid orbital is the formation of IF7 molecule. IF7 molecule, which is called as an interhalogen molecule, that is where the two halogen atoms are combining together. So IF7 molecules, so here the iodine is a central atom whose atomic number is 53. So electronic configuration for this is 5, the outermost shell configuration is 5s2 and 5p5. So 5s2, 5p5, that means 5s have the 2 electron and the 5p is having 5 electron. So 1, 2 and 3, 2 and 2. So here the total number of half-filled orbital is only 1. So in that case the electron will excited and electron will excite to the same shell, higher energy level of the same shell. So it's a d orbital. Then iodine in excited state. Iodine in excited state, so electron from the half-filled orbital will start exciting to the electron to the orbitals, empty orbitals. So here if the electron is exciting from here, so we will have total 3 half-filled orbital. If the electron excited from here, we will have total 5 half-filled orbital. And from this, we will have total 7 half-filled orbitals. So all the paired electron will undergo excitation process. So finally we will have 5s1, 5p3 and 5d3. 5s1, so s will have 1 electron, p have 3 electrons and the d will have 6 electrons. Sorry, d will have 3 electrons. So 1s, 3p and 3d hybrid orbital, 3d orbital undergoes hybridization. So in hybridized state, we will have total 7 orbitals in the outermost shell of iodine. Electron distribution will be same. So 7 half-filled orbitals. So now the iodine is ready to form a 7 bonds with the 7 fluorine atoms. So again we have only the geometry because the d orbital is involved. So we are not expected to draw, or we are not having the overlapping of the molecule. So iodine at the center, 7 fluorine atoms are there. First fluorine, second fluorine atom, third fluorine atom, fourth, fifth. So these are the fluorine atoms, I can say, which are belonging to the same plane. And these 5 fluorine atoms are forming a pentagonal geometry. And there is a 2 fluorine atom which are perpendicular to this and which will make it pyramidal shape. So 1 fluorine and the second fluorine. So this is IF7 molecules, that is iodine IF7 molecules, where 5 fluorines are at the equatorial position while the 2 fluorine are at the axial position. So we did certain type of the hybridization. Out of which the first one was sp3 hybridization, that is total orbitals was 4, and the shape of if any molecule is undergoing sp3 hybridization and having no lone pair electron, then its shape is going to be a regular tetrahedral geometry. Means the shape will be tetrahedral and the bond angle is going to be 109 degree 28 minutes, or I can say 109.5 degree. Then if any molecule undergoes sp2 hybridization, then it is going to be a trigonal planar, it will have a trigonal planar geometry and the bond angle is going to be 120 degree. If any molecule is undergoing sp hybridization, then the geometry is going to be linear and the bond angle will be 180 degree. If it is sp3d hybridization, then the geometry is trigonal bipyramidal and the bond angle is 90 degree and 120 degree. There are the 2 different types of a bond angle as we saw in the case of PCl5 molecule. And if it is sp3d2 hybridization, then the geometry is octahedral. The example for this, we did SF6 molecule. the bond angle is 90 degree. If we have sp3d3 hybridization, then the geometry is pentagonal bipyramidal, and the angle is 90 degree and 72 degree. If there is a sp2d hybridization, then the geometry is square planar and the bond angle is 90 degree. Now in an exam, generally they give the any molecules and the question is asked like the hybridization. That molecule or the example which is given, it may be the example which we solve or some other example whose shape either the hybridization is asked. So if for any molecule how to calculate the hybridization, that is which any molecule is undergoing which hybridization, how to know. So here we have a formula for calculating the hybridization of any molecule, that is number of hybrid orbital is equal to the formula we have the half of V plus M plus minus C plus A. V plus M minus C plus A. Now what is V here? The V stands for the number of valence electron. Whatever the calculation we are doing, it is only for the central atom. So this formula we are using for the central atom because the central atom only undergoes hybridization. So what is V? It's the number of electron present in a valence shell in a central atom. M stands for the number of monovalent atom. Number of monovalent atom bonded to the central atom. C stands for if the molecule of or if the ion is in charge, if the compound given is a ion and if it is a cation, then it is going to be a charge on cation. And if the compound which is given is in anionic form, that is anion, then it is going to be A is nothing but the charge on anions. So with the help of this formula, first we calculate for a given compound that it undergoes which hybridization, and on the basis of that we decide the shape and other things. Number of hybrid orbital. Suppose after calculation if I got the answer 4, then for 4 we have this hybridization sp3. This let's see the certain example. The first one is a SO3 molecule. SO3 molecule undergoes which type of hybridization? So for SO3 here I can say the value for V, the number of valence electron for sulfur is sulfur whose atomic number is 6, so its configuration is going to be 286, that is valence electron is 6. Oxygen, sulfur is bonded with the oxygen which is a divalent atom, so I can say the value of M, the number of monovalent is 0. Generally the monovalent atoms either it is going to be a hydrogen or it may be some halogens. Then C, it is neither a cation nor the anion, so being a neutral molecule, C and A value is also 0. So the formula for the hybrid orbital is equal to half of 6 plus 0 minus 0 plus 0, that means it is going to be 3. So there are only 3 hybrid orbitals, so it will undergoes sp2 hybridization. So SO3 is a molecule that, so if the question is what is which SO3 undergoes which type of hybridization, then answer is going to be that it undergoes sp2 hybridization. The second example, suppose I have SO4 2 minus, that is sulfate ion. Here the valence shell, again the sulfur is a central atom, so number of electron in a valence shell is 6. Again oxygen being a divalent, so M is equal to 0. Then it's a anion. This species is in anionic form carrying a -2 charge. So here I can say C will be 0, but A will be equal to 2. That is A stand for the charge on anion. So here I can write the formula for the number of hybrid orbital is equal to half of V, V is 6, plus M 0, minus 0, and then plus 2. So it is 8 by 2, that is 4, and if it is 4 then it undergoes sp3 hybridization. So I can say that here the sulfate ion undergoes sp3 hybridization. Then the third example, suppose I have carbonate ion, CO3 2 minus. If it is CO3 2 minus, then hybrid orbitals is equal to the valence electron, the carbon whose atomic number is 6, so 2, 4, that is 4 in the outermost shell. Oxygen not a divalent atom. Cation, it's a anion, so this is cation C value is also 0, and anion, so it's a 2. So half of 6, again it undergoes, so 6 upon 2, that is 3. So it undergoes sp2 hybridization. Then fourth which we have is PF5 molecule. PF5 molecule, the phosphorus atom. The phosphorus, 5 electron in the outermost orbit. Fluorine is a monovalent atom because it carries charge -1. So the number of monovalent atom, that is M, is equal to 5. C and A both is equal to 0. So it is going to be half of, that is hybrid orbital is equal to half of 5 plus 5, that is 10 upon 2, and if it is 10 upon 2, that is total number is 5, and if total number is 5, so 5 half-filled orbital means I can say it undergoes sp3d sp3d hybridization, and will have trigonal bipyramidal shape. Then fifth, NH4 plus ion. NH4 plus ion, nitrogen, valence shell, number of electron in a valence shell is equal to, here in case of nitrogen, 5. Hydrogen is a monovalent atom, so 4. It's a cation, so C is equal to 1, A is equal to 0 here. So hybrid orbital is equal to, we have half of 5 plus 4 minus 1 plus 0. That means 8 upon 2, that is 4. 4 means sp3 hybridization. This is sp3d. But at the same time, this formula is not applicable in all the cases. Generally, suppose if I am having a molecule of certain more things for writing the configuration. If the carbon undergoes single bond formation, that is alkane, then it is always sp3 hybridization. Same thing I can say for nitrogen also. If all the bond formed by the nitrogen is a single bond with a lone pair electron, then it undergoes sp3 hybridization. But suppose if the carbon undergoes double bond formation, then it is sp2 hybridization. And the same thing for, I can say, nitrogen. This is amine. If the nitrogen form a double bond, that is imine, then it again undergoes sp2 hybridization. And if the carbon undergoes sp3 hybridization, triple bond formation, then it undergoes sp hybridization. Similarly, if the nitrogen also form triple bond, generally in case of cyanide, if the nitrogen is forming a triple bond, then in that case, the nitrogen also undergoes sp hybridization. So in addition to this formula, just keep in mind that if the all the bond formed by the carbon is a single and all the bond formed by the nitrogen is single, then sp3, carbon-carbon double bond, that means carbon undergoes sp2 hybridization. The same rule is applicable for the nitrogen. And if the carbon forming a triple bond, then sp hybridization, and the same rule is applicable for the nitrogen. Many times this formula related to these compounds and these compounds gives the wrong detail. That's why this is the additional information to this formula.